Hello, this is Lisa Seidman, and this is the third in a series of videos about common calculations in the biotech workplace. In this video, I'm going to continue talking about calculations involved in solution making, and I'm going to finish up the video introducing some of the common ways in which concentration is expressed in real-world settings. But before we go into the lab, let's go into the kitchen and make some coffee. Coffee has two components: the solid, that's the coffee grounds, that's the solute, and water, which is the solvent. And we know that in order to make good coffee that tastes the way we want it, we need to know how much solute and how much water to add to get it to be perfect. So we have two how much questions, solute and solvent. I want to point out that actually coffee is not a true solution in the sense that a chemist would use the word, because it's not entirely homogeneous. Coffee is not entirely dissolved. But for our purposes, it's analogous to a laboratory solution. So now moving into the lab, let's suppose we have a protocol. It calls for 50 mils of sodium chloride, that is the solute, at a concentration of 10 mg per mil. So our question is, how much sodium chloride are we going to weigh out to get this solution? Okay, we know we want 50 mils, and we want a concentration of 10 mg per mil. So using unit canceling, we can say we need 50 times 10 mg equals 500 milligrams. We could also use a proportion method. So we know we want 10 mg per each mil. We put our equal sign and our line. We have to have the same units in both denominators, so 50 mils will go here, which means our unknown goes here. So we can cross multiply. We have 10 mg times 50 mils equals 1 mil times question mark. Mils will again cancel, and we will get question mark equals 500 milligrams. But there's one more calculation we have to do here, because balances, that is laboratory scales, are not calibrated usually in terms of milligrams. They're calibrated in terms of grams. So we have to convert 500 milligrams to grams. Well, we want 500 milligrams, and we know that 1 gram is equivalent to 1,000 milligrams. So using unit canceling, we can say that 500 milligrams, we divide it by 1,000, equals 0.500 grams. Okay. Now that we know that, we know how much we want, now we can go to the storeroom and we can find the sodium chloride. It's going to be a solid, crystalline solid, much as it looks in the kitchen or in your house. We're going to weigh some of that out, so we're going to go to our laboratory balance. So here we are, weighing it out, not quite at 0.5 grams yet, so we have to add a little more. And once we've weighed out the proper amount, it can be dissolved in water, that's the solvent. And here it is being dissolved, but it is not yet being dissolved in 50 mils. It's being dissolved in somewhat less than 50 mils. Now once it is dissolved, then we can worry about how much solvent. So to do that, we're going to use a graduated cylinder. So this is a device, it's made of glass, this one could be made of plastic, and it's calibrated. This is 10 mils, 20 mils, 30 mils, all the way up to 50 mils. What we do is we take the salt that's been dissolved, pour it into the graduated cylinder, and then add water until we reach the 50 mil mark. And at that point we know that we have a solution in 50 mils. That's called bringing to volume. We bring it to the final volume we want. BTV, bring to volume. In this case, 50 mils. Now, you might also see this written as QS, which is fancier because it's Latin and it means quantum sufficit. But it means the same thing as BTV. These two things mean the same thing. All right, so now that's how we make a solution. But what does it really look like when you see solution recipes in the real world? Well, here is what it might look like. This is a quote from a real article of people who were working on a real biotechnology product. So let's look at this slowly to understand it. The first line says cells were lysed on ice, that means cold, with cold REPA buffer. So the first thing we have to imagine is, okay, we got a bunch of cells, They're growing in a vat, in a beaker, in a container of some kind, a bunch of cells. They're going to be isolated and they're going to be lysed, which means broken open, to release whatever's inside of them. And in order to do that, the scientists use REPA buffer. Now, the part that's in parentheses here, all of this part that's in parentheses is the recipe for how you would make REPA buffer. So it's a recipe somewhat like you might have in the kitchen. You go to bake a cake and it might say you need a cup of flour, I don't know, you need some sugar, cup of sugar, and so on. But note that in the kitchen, these are amounts, a cup of flour, a cup of sugar. These numbers here are actually concentrations. Now, so far the concentrations we talked about, like 10 mgs sodium chloride per 1 ml. This is a ratio. It looks like a ratio. It's got a line. It looks like a ratio. This is also a ratio, but it doesn't look like one. So in a subsequent video, we're going to talk about what this means. And by the way, the little m, big M means millimolar. It's an abbreviation for millimolar. So the first component here is our friend table salt. And it is present at a concentration of 150 millimolar. The next component of this REPA buffer is 25 millimolar tris. And then there's the next component is 1% NP40. 1% is also a concentration. We'll talk about this W/V in a later video. So this is 1% W/V of NP40 is the next component. Then we have another component, which is 1% W/V of sodium deoxycholate. And then finally, we have another component, which is 0.1% SDS. So there are 5 components. 1, 2, 3, 4, 5. So there are 5 components in this buffer. Just like a cake has more than one component. There are 5 calculations for one for each of these components involved in making this buffer. So if you were going to make this buffer, you would need to do 5 calculations. And those are the calculations that are the subject of our next videos. We're going to start with this one. So stay tuned and we will learn about making recipes that call for a certain percent of a solution.